Hey, so I'm Jordan Halterman. I'm a member of the technical staff at ONF. I work on distributed systems in ONOS, wrote Atomics, and so I maintain a lot of the distributed primitives, distributed stores, and things like that in ONOS. So I'm going to talk today about, well, this isn't so much a talk about how to build scalable applications in ONOS, but more a talk about how not to build them. And so I'll get into what I mean by that. So just a brief review of what a distributed application in ONOS looks like. So this is going to be sort of a code-centric talk. So lots of code and discussion about what's good and bad about these coding patterns. So one of the ways applications sort of manage state in ONOS is by interacting with core services. For example, this sort of shows the flow rule service being used. And when something like flow rules are pushed into the flow rule service, what happens is there are various distributed protocols that happen behind the scenes, and the way that an application interacts with some of these services can impact scale. And then the other sort of way that applications do state management is through the use of distributed primitives. So, and this sort of shows what the rat service looked like in the past, which just creates distributed data structure and uses it to store and replicate some state. So distributed primitives are sort of like a high-level interface designed to make distributed systems or distributed algorithms sort of accessible to application developers. But the problem with these is that many of distributed systems has a lot of pitfalls. There are lots of gotchas in distributed systems, and primitives can't really hide everything. And so, for example, time still doesn't progress at the same rate on all the nodes. The network still introduces, and the protocol still introduces a lot of latency. And an argument can even be made that sort of using distributed primitives may even make some of these types of problems more likely to occur and more difficult to detect. So, as you guys have heard over the last over the last year, as Thomas was saying, we've been working on trial deployments and production deployments, and through that work, we've learned a lot of lessons about how best to manage distributed state in ONOS. So we've done a lot of scale testing, found a lot of issues, and most of these issues have been related to how distributed state has been managed in applications or core components. But the good thing is that most of these deficiencies, they can be corrected by good development practices. And so this talk is basically sort of taking some lessons, so 6 lessons from our work over the last year, sort of working on trial deployments and production on how to ensure that your applications, and even for ONOS core developers, how we can ensure that components are scalable. And these lessons are going to go sort of from most obvious to most important. So with that, lesson number 1, don't pull primitives. And this is, like I said, this is sort of an obvious one. So, so a read on a primitive or an operation on a primitive has a cost. And so that cost is usually for most of the protocols in ONOS 1 to 2 round trip times. But ONOS features a rich event framework. When state changes occur in the system, almost all the time there's some event that you can listen to rather than trying to monitor the system for state changes. You can react to them. And so so optimally you want to rely on the event delivery systems to react to state changes in the system. And there's really no downside to doing so because we put a lot of work into ensuring that events are delivered with the same sorts of consistency guarantees that other operations on the distributed systems and distributed primitives are provided. So for example, this is an example of it's sort of a contrived example of some code creating a leader elector. So the leader elector is a distributed primitive that actually underlies mastership elections and things like that in ONOS. And so one way you could wait for a leader change is just to, in a loop, check the leadership service for changes to the state. And so what's happening then is a bunch of operations, get. And when these things are occurring, there's a lot of network traffic, various distributed systems protocols going on behind the scenes. And so the optimal thing to do is to just wait for a notification, obviously, and that's what this, so ONOS provides APIs like this all over the place. So in this case, rather than polling a leader elector, we're adding a change listener, which basically, when a leadership change occurs, some RAF state machine somewhere will notify all the listeners and allow you to react to it. So that's the most obvious one, but it's still an extremely important rule. So on to lesson number 2. And this is related to the last one. Don't block the event loop. So this is something that we saw in production systems and trial systems a lot. And it's really important, and it's not always obvious when it's happening. So what is an event loop? So I talk about events being delivered to listeners. Well, those events are delivered on an event loop, and basically an event loop is a single thread that reads through a queue of events and calls those listeners. And the reason that these event loops are single-threaded typically is because we're ensuring that events are delivered in the same order in which they occurred on some other node, usually on some other node in a RAF partition or on a master node or something like that. And so, but the problem is, since it's a single thread, when an event is received and some code, the event listener does a blocking operation, you're actually blocking the event loop, preventing other events from being delivered. And there's actually, in some cases, what the result of this that we see in production systems is that, so there's a core component in ONOS called the core event dispatcher that will actually go around interrupting threads when they block the event loop. And so again, a code example. So this is sort of a contrived example that's creating a consistent map and then storing mastership changes in the consistent map. And so it's not totally obvious that there's anything blocking happening, but so this event that when the mastership service is publishing an event saying, here's an event, a mastership change happened, this is happening on an event thread. So it's a single event loop. And then, but when you use a primitive inside one of these threads, you're actually blocking the event loop. And it can even get even worse where sometimes this type of code actually uses another core service that inside of it has a primitive usage that ends up blocking it. So the best thing to do is often to just assume that if you're calling a primitive operation or calling a core service, then you're potentially blocking the event loop. And so the solution, so I'm going to propose some solutions here, is to, and obviously this is often the fix that we use for these issues when we found them in production systems, is to create your own event loop just for your application and then offload to that event loop. So this is basically creating a separate single-threaded executor and then calling it to get the event off of the core event loop so that it won't be blocked. But there's even a slightly better solution to this, which is, so all the distributed primitives in ONOS, there's a synchronous version of a primitive and an asynchronous version of a primitive. And so this is actually an example of, if you look at the actual creation of the consistent map, it's actually building an asynchronous map. And by creating an asynchronous primitive, you can use it in an event loop thread, and you won't be blocking it because it's asynchronous. Yep, so those are asynchronous calls inside the event loop thread, and since they're non-blocking, it's not a problem. So, lesson number 3, avoid hotspotting. So this is where we get into how state is distributed in the ONOS cluster. So a lot of the state, especially, so most of the primitives in ONOS are consistent, and the way that state is typically scaled is through partitioning, which I'll talk about a little bit. But the problem is that not all primitives can be partitioned, and these problems can sort of create what we call hotspotting, which is a lot of load on a single node, and it reduces scalability a lot. And so the solution is to limit or optimize usage of those types of primitives, and I'll show an example of how that can be done. So again, the state space for a lot of the state in ONOS, or the consistent state at least, is split up into partitions. So if you create something like a consistent map, that map is spread across all these different partitions, and actually what a partition is a RAF cluster. And if you want to come to my 5 o'clock talk, I'll talk a lot more in depth about that. But so, for example, in the example of a consistent map, what you might have is, for example, keys A through E stored in partition 1, F through J stored in partition 2, and this sort of provides you scale by reducing the overall memory consumption, but also improves throughput, because those partitions then are evenly distributed among all the hosts in the cluster. So, for example, partition 1 might be replicating on nodes 1, 2, and 3, whereas partition 3 is replicating on nodes 3, 4, and 5. And this allows both the actual servers to be spread across all the ONOS nodes and for leaders to be spread across the ONOS nodes, and that's what allows us to scale write throughput. So, but again, not all primitives are horizontally scalable. So not all primitives can be partitioned like a map. But maps are, like things like maps and sets are easy to partition. But here's an example of a primitive that's not easy to partition. And this is actually another example that was taken from the code from one of the issues that we ran into with host probing in particular. So sometimes a way to generate, for example, a UUID in the cluster is to just create an atomic counter, which is a consistent primitive. It's a good way to create a globally unique number because it's backed by a consensus algorithm, and you're guaranteeing that every time you increment it, you're getting a unique number that no other node will get. But the problem is this, so counters are actually a really difficult problem in distributed systems. It's kind of weird because it's such a simple thing, but since it relies on order, the only way to do this in this particular architecture, there are some other algorithms for it, but I won't get into that. But so, I mean, a counter relies on order, and we only get order within one RAF partition. And so the counter necessarily has to be mapped to one of the partitions. And so that, when you're doing this, if you're using the counter a lot, generating a lot of UUIDs, then you're putting a lot of load on one partition, and it's just not scalable. And so I mean, optimally, you can find a different data structure to use instead of using counter as a UUID, but you can also think about optimizing your usage of the primitive. So, and this is one way you can do this. So every method call, I mean, if we go back to the counter example, essentially every time increment and get is being called, that's a write to a RAF partition. And so the way you can help improve the scalability of this is to reduce the number of writes. And this is actually an optimization that we do. So rather than, if you just want a UUID, rather than incrementing the number every time you want a new number, thus writing to a RAF partition, just reserve a batch of numbers and then do the incrementing locally, because a UUID doesn't require order across all the nodes. This is a fine solution. And in this particular case, there's actually a primitive that does just that. So there's actually a little known primitive in ONOS called Atomic ID Generator, which actually does that exact optimization. So lesson number 4. Optimistic locking is your friend. And so this is where things get a little more complicated. What is optimistic locking? So optimistic locking, I mean, it's a method of locking in distributed systems for cases where you don't have a high amount of lock contention. That you know, in the best case, optimistic locking basically costs nothing, and I'll show you how it's done. So, for example, for an example of a case where you could use optimistic locking, so this is actually taken from the route store. It's actually, this isn't actually the implementation of the route store, but a modified implementation to show how this works. So if you had, for example, a consistent map with a set of routes, and you wanted to update it, in order to update it, you'd have to, you know, read the set of routes, initialize the set if necessary, add a route, and then write it back. But these are two distinct operations that this produces a sort of consistency issue, because by the time you actually write the updated routes, some other process, some other node could have changed it. And so optimistic locking is a cheap technique to be able to make two operations like this atomic. And the way that that's done is, and this is actually the reason that the consistent map interface, if you look at it, it returns versioned objects, and this is why. So you can do optimistic locking. So basically the idea is that when you read a value, you get back a version number, which is something that's provided by Raft. So it's something that's a strongly consistent number that's guaranteed to not be used by any other entry in the map. And then when you do the second update, you send the version number back and sort of do a check and update. So the actual Raft state machine that controls the consistent map will only write the value if the version hasn't changed or some other process hasn't changed it. And so in the code, this is what that actually looks like. So rather than just doing a put, we do a replace. And so replace is a special method on consistent map that allows you to provide a version to do just that, to only update the value if the version number hasn't changed. And this is how optimistic locking works. So actually in ONOS, there are implementations of optimistic locking on the consistent map interface. And this is exactly what's happening when you use the compute methods on a consistent map. So obviously we want every method on consistent map to be atomic. And so the implementation of compute and compute if absent and compute if present uses this exact technique behind the scenes. So it'll read the version, apply the compute function to the value, and then attempt to write it back and retry. So lesson number 5. Optimistic locking is not always your friend. So there are actually problems with this. So like I said, optimistic locking is awesome and performs really well in the optimal case, but it can become really bad. And this is in cases where there's high contention. This is actually something we also saw in scale testing. So when you're having scale issues and you're using optimistic locks or compute methods or whatever, it's worth looking into whether the optimistic locks are causing those problems. And so I'll show a couple of options for how to resolve this. So going back to the example of optimistic locking, so if there's high contention, well, like I said, what's happening is the compute method is reading, getting a version, and then trying to replace with that version. But what happens when there's some concurrent process trying to do the same thing is one of the two has to fail. And so if you have a lot of concurrent processes trying to use optimistic locks, you get constant failures, constant retries, and ultimately you end up doing more writes than you would otherwise do if you used pessimistic locks. So there are sort of two types of locks in distributed systems: optimistic locks, like we've seen, and pessimistic locks, which it looks like a traditional lock. So I think it was like in 1.13 we added a pessimistic lock primitive. And so one solution to this, if you have a lot of contention on a shared resource, is to use a pessimistic lock. And what you get from pessimistic locking is a deterministic number of operations that must occur in order to update a primitive. So it's always going to be one write to a Raft partition for the lock operation, then one write to unlock the lock. But even more optimally, and this was actually the solution that we ended up implementing for the routes service when we had this issue with optimistic locking, is to just use a better primitive. So the route service or the route store was using a consistent map with a set of route values, but what that is a consistent multi-map. And so by using a better primitive, what we're actually doing is pushing more of the logic into a replicated state machine that's always consistent and always requires a single write. And so something like the routes.put operation always takes a single write. And this actually improves scale in the route store a lot. And so on to the last lesson. And this is the most important: exploit data locality. And this is something that's done all throughout ONOS. It's probably one of the most important things in scaling distributed systems. So obviously the network is expensive. Distributed primitives are extremely expensive, even though we're doing scaling techniques like partitioning or sharding. these algorithms are still extremely high latency, and it's always best to do things on a single node if possible. And so in some ways to do that are the ways that we do that in ONOS is often do like for state that's related to the southbound or to the network, we do a lot of computation on the master nodes. So just send something to the master has an up-to-date view of all the state related to some device, and it can do computations locally. And like I say, this may be lesson number 6, but it's rule number 1 for scaling. So one example of another issue that we had was, for example, we had a node sending a packet south to the network, and it would get back sort of a result on another node. And so one way that you can synchronize and sort of share state and coordinate between the out and the in is to use a distributed primitive. And this is a perfectly valid use case, especially for consensus, because it provides a single system view. Node 1's update is always guaranteed to be seen by node 2 immediately. But this is obviously extremely expensive, and we had an issue in the host probing algorithm actually sort of related to this. And so the best thing to do is find some way, even if you have to broadcast the resulting message to all the nodes, it's way more optimal than using a distributed primitive between the two. And so my best advice is to avoid using distributed algorithms as much as you can. Yeah, so just to review once more. Don't pull primitives, don't block the event loop, very important. Avoid hotspotting. Use optimistic locking for low contention, pessimistic locking for high contention or a better data structure, and data locality is king. That's it. Questions? What time is it?
You got 10 minutes.
Cool. Yes.
I have one question. So, in that pessimistic lock, is that auto-closable?
No. No, not that implementation, no. Also, if you have questions, like I said, about the protocols that are being used in these cases, come to my 5 o'clock talk, because I'll get really into depth in them for an hour.
So there is a primitive in atomics for east-west communication, synchronized east-west communication.
Yep.
For example, you invoke an API. Basically, there are southbound devices are available to different nodes, and application leader is on one node. He want to do something on the other node to the device.
Yep.
So there is a mechanism you can invoke a synchronous call to that node so that it pushes the configuration device and return back the result in the same call. So, but there are timeouts happening on that call. At times we see that in different environment, timeout value is different.
Yeah. So this is something that's actually fixed in the latest releases, which I'll talk about a little bit later. So there's sort of a conflict actually between Raft and the other protocols that are happening external to Raft, and they're all sharing the sort of same communication mechanism. So the problem is Raft works best when you can detect failures and retry quickly, and that's how a lot of distributed systems protocols are. If you get a timeout quickly, you can retry and use things like exponential backoff to avoid overloading the network. And so there's sort of a conflict between, currently, because of that, we implemented dynamic timeouts that sort of react to, they scale up and down depending on the latency that's being sampled from the network. And so, but yeah, that's in conflict to a lot of things are long running or might take a long time, longer than other things that are going through the network. And so that causes problems, but actually that's why we added, in the newer Atomics releases, we added explicit timeouts, so you can set your own timeout like 10 seconds and to circumvent those problems.
Thank you.
Okay.
So I have several minutes. So.
Well, thank you.